Okay, it's about 7:30 according to my clock. Bruce, when's our speaker coming online?
Around 7:45, 7:50. So
Okay, perfect timing. All right, for everybody who's on live on YouTube and for everybody who's welcome to the March meeting of the Chester County Astronomical Society. We have a great speaker tonight, and I'll let Bruce fill you in on that in just a little bit. As we've been talking about, for anybody that's out there and isn't able to interact with us directly, we are probably going to be going back to live meetings for the April meeting. Keep posted. We'll let you know more about any changes that come on that, but I think that we'd really like to start the in-person and hybrid meetings so that those that wish to get together in person can do so. And Don, remind me to bring coffee if we start the live ones, because I'm not liable to forget. And with that, Don, would you like to show us what's up in the night sky for this coming month?
I'm going to do something a little different rather than do the same old thing. I think I wanted to change it up so we don't get in a rut. So I'm going to show you something else. How's that?
Okay.
And what I'm going to show you is some slides that I got from John Goss, who some of you I think know John, correct?
yes.
John is currently the president of the Roanoke Valley Astronomy Club down in Roanoke, Virginia. He has twice been the president of the Astronomical League. And he's an amazing guy. I've met him a couple times, and he has done so many wonderful things for the hobby, the lifestyle of amateur astronomy, that he's really been, he gives a lot of his life to it. So these slides are from John, and they are from a presentation he made for the 75th celebration of the Astronomical League, which everyone watching tonight is a member of the league, because our club is, and we invited DVAA and DAS, and every one of those clubs is a member. So I'm going to go through these slides. I thought they were worth sharing, and just to change it up from looking at the night sky like we always do. So this talks about two kinds of observing. One is at star parties, which we are starting up again. I know that a number of clubs, DVAA is going back to regular star parties. There's a club down in Northern Virginia called NOVAC, Northern Virginia Astronomy Club, and they are 1,000 members strong. Okay.
Wow.
They are, I think they're the biggest club in all of Astronomical League. So they're 5% of the league, and they're in our Mideast region. So they're a sister club of ours, really. They're starting up their events also. So let me go through these slides. I thought these were really, well, John did a great job putting these together. So observing is what it's all about. You know, a lot of us, we join these clubs and we sit in these meetings for, everyone has their own reasons. Maybe some people just do it for these meetings, which is a great thing, because we've had some great meetings thanks to Bruce this year. Some people do it because they observe on their own, but a lot of us like to observe because we go to star parties. And I'm actually trying to get away from saying star party. Some people think, when they hear the word party, they think, oh, what do you guys do? Drink beer and dance around? I tend to call them night sky observing events. I think is a better description of it. So, but observing is what it's all about. You know, this is sort of what it looks like at a stargazing event, like whether BRC, or if we get back with, we have some arranged with Hoops Park again. And so this is what it looks like as the sun setting, probably looking at Jupiter or Venus here when the event starts. So you got to think, you know, who could be waiting in line to look through your telescope or binoculars, or maybe you're just there. You don't even have to bring equipment to one of these events. Just come out to hang out with club members. Who could be waiting in line? Could be young boy and girl, parents in tow. And, you know, some of these young kids are amazing. They are just know everything about Saturn or the other planets. They're really fun to listen to. Or it could be a teenager sort of looking bored, iPhone in hand. That's what he's looking at, been dragged along by somebody, you know, acting disinterested, but maybe inside, maybe they know there's something going on they want to see here. Or it could be a whole family of immigrants that are standing in line. I know we've had many from the Latin community come out in Westchester to Hoops Park. and they want to see the moon. And these kids know this stuff. Or it could be some people with motorcycle helmets. Maybe it's some bikers that they've heard about this somehow or drove by and, jackets with chains, and maybe they want to go look at Jupiter. Or a doctor maybe who's read about this, wants to see Mars with his own eyes. It could be all kinds of folks. It could be a teacher, a young couple on a date. Or we've had many people in their 80s come out who wanted all their life to see the first view. I know when Kathy helped us one time, the Barb and I out at a assisted living facility. Those people were in their 80s and 90s, and some had never looked through a telescope. But it's a whole microcosm of humanity. It really is. There's something special about getting together like this in a public event. So after they see these things, if you could hear their thoughts, what would they be thinking, do you think, or saying? The kids would be pestering their parents to come back. I've been at events where kids come up, they look through the eyepiece and go, "Hey, Mom, it's outer space." They're really fun. It could be a teenager texting his friends how cool Saturn was. Or the family just being so thankful that they could see something they've never seen before. Or the motorcyclist, maybe get a thumbs up from them if you're lucky. And the doctor would be thinking how small we are in this fantastic universe. So, and it's because of these kind of efforts, people have seen further with their eyes and more importantly with their minds. And how does it make you feel? I know how it makes me feel. It makes me feel really great. I would say warm inside, but sometimes it's pretty cold at these events. So it helps warm me up when you see these people appreciating, what you've done when you come out to call it a star party or a night sky observing. It's something. If you haven't done it, you should come out. Whether you have a telescope or not, just come out and join us. Hoops Park will be coming up, I think, in May, and we'll have other ones. Friday Night Lights is on the schedule for this year.
Yeah.
That's an amazing event with hundreds of people. And I've talked to Westchester Recreation. If I can determine that the moon and a planet or two will be at the right spot, we're going to do sidewalk astronomy again in Westchester. And that was a blast. So I'm trying to encourage people to come out and join us. Whether you bring a scope or not, just come join us. So now it's another kind of observing that John put these slides together. And this is more of a personal experience. So here's a refractor set up on an equatorial mount. Okay, so maybe like we've been having, after a lot of bad weather, you finally get a clear night and you're lucky enough to be someone with a telescope, so you set up. So night descends, the enveloping dark like blinders, and you focus your thoughts to the sky. So this is a star map. It looks to me like perhaps out of the Sky and Telescope Guide. This is a section of the southern sky we see in like July and August. Scorpius here is one of our favorite little objects that is low in the sky for us, but we had great views of this at Cherry Springs. This is the Northern Jewel Box. Two of my favorites here is M7 Ptolemy's cluster and M6, the Butterfly cluster. So this is a great part of the sky. So you got your scope set up, you're starting to plan, you're not observing. Okay, a feeling of mounting excitement takes hold of the sound and feel. This is a polished metal eyepiece sliding into the focuser. And there's a sound to that when you do it, you know it and you feel it. It just slicks, it's like snicks into place. It's so nice. These things are so highly machined. And then you have the silent buttery turn of the focuser, bringing the stars into view. You've got anticipation grows further. You direct the tube toward the evening's first destination. In this case, they picked out Messier 62. It's a globular cluster, something we can see, in Chester County skies without a problem. Stars sweep by as they slowly sweep the area. So this is a sketch. I think it's a sketch that John made. The way these are typically made, you do them on pencil lead on paper, scan them, and then reverse the colors. So it ends up being white on black instead of black on white. So voila. Near the edge of the eyepiece, the field glows slightly grainy, but mostly fuzzy ball of light. This is a pretty good approximation of what it looks like in the eyepiece of a telescope. Probably better than some photographs do. Okay, so excitement turns to wonder, pondering what you can see under higher magnification. See numerous faint stars dotting its dull glow. Its bright smeared core, slightly off center, the cluster floats among unnamed star fields. And you think, what if you lived on a star in this cluster? What would it be like lying just a few thousand light years above the center of the Milky Way? The view must be grand indeed. Thousands of brilliant stars. Think about 1,000 stars like Sirius in our night sky, or like the brightness of Venus is. Okay, pepper the sky with nearby globular clusters glowing in the distance. And the globular clusters you see in the distance, those stars are 5 billion years older than our star, the sun. So you see some ancient things in the sky if you could see from here. And so the globular clusters typically are about 10 billion years old, the ones we see from here. So after seeing all that, how does it make you feel? Okay. And this is what the Astronomical League calls the authentic observing experience. Okay. That's what they call it. So it's personal, gives satisfaction, peace, and a sense of enlightenment. So 75 years, the Astronomical League does get it. What's the secret? It understands people's need to personally experience the wonder, beauty, and mystery of the heavens.
Sorry.
Okay. So I just wanted to share that to show to people. I thought it was, with John, you did a great job preparing that for the 70th anniversary of the league, and I didn't want to have it go unshared. So
Really nice, Tom.
Bruce, I'll turn it back to you.
Dave, any other announcements before we get going?
I'd like to say, I just
Okay.
want to mention one thing on to Don's little program there was many years back, I organized the 60 millimeter telescope club star party up at Cherry Springs. And this is an organization I have had for a long time. I have people from all over the world. And we had an official star party up there. And one night, a pack of motorcyclists came roaring in and was riding around, checking everything out and everything else. And they stopped at our group. And we invited them over to look at our through their telescopes. And believe me, they really enjoyed it. It just felt good when they said, "You guys are okay." And then they hopped on their bikes and rode away.
So no other announcements at this point, as far as I'm concerned. Since COVID kind of came back with a vengeance with the latest variant, I've kind of been holding off on meetings. I know that some of us have some reservations about, especially getting into public places, but I think next month would be a good time for a meeting. Execs, please let me know a couple of good dates, and we'll see if we can get that all together. And with that, I'd like to turn it over to Bruce, because we have an exciting program coming on tonight, and this is going to be great.
Thanks, Dave. Thanks. So again, it's a real privilege to introduce Dr. Benjamin Huckman tonight. He is a robotics engineer from JPL, and Ben did his PhD work at Stanford. He has worked pretty much his entire career on developing robotic systems and platforms to explore a variety of celestial bodies, from asteroids to comets, moons, planets. And he is going to tonight present several different scenarios in his talk, which I think whether you're geared more toward engineering or more toward pure planetary science, I think you're going to find this really, really exciting. I think it's pretty cool. Ben is actually a local guy. I didn't realize this until we started to talk a bit. He was, I think he grew up in Hocassin, Delaware. He went to school, the charter school in Wilmington. He was an undergrad at UD. And I believe his mom and much of his family still lives in Westchester, so we have to hunt them out, okay? I just thought it was kind of almost amusing that Ben said it was the sky in this area that inspired him to pursue a career in space exploration. So if the Westchester sky did that, I can only imagine.
That's funny.
But at any rate, it's a real pleasure to introduce Dr. Benjamin Hockman, and I think he has a really cool presentation for us tonight. So, Ben?
Hello, everyone. Can you hear me?
Yes.
Yep.
All
And
right.
one quick announcement. everyone, please mute yourself if you would. If you have a question, just unmute, but if you don't mute yourselves, I will from here, okay? Thanks.
Yeah. And we'll see how long we go, but I'm happy to be interrupted along the way if you guys have any questions. I'm going to kind of cover a variety of topics, so there might be some good points to stop and ask for questions, but feel free to interrupt me also. So yeah, let me share my screen here. All right. All right. Are all the mics good? Okay. All right. Well, thank you so much for having me, and thanks for the introduction. Yeah, as Bruce said, I'm a robotics technologist at NASA Jet Propulsion Lab, but my origins are very much around where you guys are at, and it's interesting looking back how I got here. So I kind of didn't know how to structure this talk, but I thought the most logical story to tell from my perspective is really just my journey. There's a million things going on in space, and so I decided to give you kind of like a little bit of breadth of what's going on, but then focus on a few really cool projects that I've been involved in and sort of how I got my start. So the first thing you might notice is that there's no Mars rovers on this title slide here. That's because since I'm a technologist, I'm really very much concerned with future concepts of exploration of bodies we haven't been to before. And while I do work some on rovers and the autonomy for them, a lot of the concepts I get really excited about are the ones that are totally foreign and really unique systems for the space environments that we're operating in. So I'm going to kind of spotlight these three concepts: the exploring Venus, small bodies, and Europa. So yeah, this is where I'm from. Like Bruce said, I could throw a rock to Pennsylvania from where I grew up, and I have a lot of memories going to Kennett Square and the mushroom smell around there. And so yeah, until I was 21 years old, I was born and raised in this area. My mom's from Westchester. A family has since moved to Colorado because that's where my dad's family is, but I still have a lot of family in the area. And I got to say, I grew up, both my parents worked at DuPont, which is one of the big companies in the area. And they were career statisticians that worked for DuPont. And growing up as an aspiring engineer in Delaware, the options seemed to be mostly around these big companies like Gore, DuPont, and you would spend your whole career there. I certainly didn't know anyone that worked at NASA. And I did have a few, I'd say, formative star experiences. There were a few meteor showers that I remember particularly well, where my mom would take me out onto the driveway and just be amazed at all the shooting stars. I did get to go to Mount Cuba as a kid and look through some telescopes there. That was really interesting. And then we had a road trip sometime in high school out to Yellowstone, where of course the dark sky is just incredible and you can see the Milky Way. So, but it wasn't until I considered going to grad school that the world of space opened up as an opportunity or as an idea that I might pursue. So I moved in grad school to Stanford. At the time, I was really just more generally focused on robotics, mostly for terrestrial applications. But as soon as I got to Stanford, I got involved with a lab that was collaborating with NASA, JPL, where I'm currently at. And there was a really cool project that had just started out when I moved to Stanford in the Aeronautics and Astronautics department there. And the problem statement was essentially, how do we explore tiny worlds in the solar system? You know, we've sent humans and cars that they can drive to the moon. We've sent a number of rovers to Mars, and they more or less look the same. But there are thousands and thousands of other bodies in the solar system that are much smaller. These can be asteroids, comets, small moons, and the gravity is extremely low. So the challenge is, how do you develop a rover for a body that's whose gravity is so weak that you would just fly off if you decided to try and drive on it? So here's just kind of a snapshot at the variety of small bodies in our solar system. Of course, they're all over. There's a big cluster around the main belt between Mars and Jupiter, main belt asteroids, but we have a lot of asteroids in our local neighborhood, and then many comets that come in from much further away, as I'm sure you all are aware of. So this is probably not that new to you, but but once they become resolved objects, not just, a point of light in a telescope, they become very interesting, and you start to appreciate the real variety and challenging terrains that these bodies present for doing surface exploration. So the real moonshot goal here was to develop a rover of sorts that could bring the same kind of capability to explore the surface of small bodies like we've done on Mars. So to skip ahead for a lot of concepts that we thought about that didn't work, what we always came back to was the idea of hopping around on small bodies, because the escape velocity on these bodies is quite small. So all you would have to do is push a little bit on the surface, and all of a sudden you're hopping 100 meters across the body. So instead of trying to get wheeled rovers to stick to the surface, we developed this hopping rover we called Hedgehog. And so this was kind of the basis of my PhD work at Stanford, essentially how to control a hopper in a microgravity world. So we're talking 10 to the minus 3 to 10 to the minus 5 Gs. So to put that in perspective, you would weigh about as much as a paperclip on these bodies. That's how weak the gravity is. So you can imagine trying to walk around where if you even just touched the surface wrong, you would fly away. So the key challenge for this project was how to control that behavior. And so the system we ended up developing was basically a box with 3 reaction wheels inside. Reaction wheels are standard actuators for spacecraft to control their orientation, their attitude. But in this case, we use them for hopping. So by applying a torque to the internal wheels in this box, a counter torque is produced that pushes on the surface and creates a hopping motion. So depending on how we actuate these internal masses, we can essentially, through this momentum exchange process, hop and tumble around the body. And the idea would be to bring some targeted science instruments to targets of interest. For example, Mars's moon Phobos. We had a concept to bring some spectrometers and cameras to investigate the mineralogy of the surface, because there's a lot of mysteries around Phobos. But this concept was really scalable to any body that's very small like this. So the basic principle is illustrated in this video. So this is a prototype I developed. And what's happening now is this internal wheel is spinning up very fast. And then we apply a mechanical brake. Let me play that one more time. We spin it up to build angular momentum inside this box. And then by applying a mechanical brake, we can abruptly transfer that to the chassis, which gives rise to a hopping behavior. That's a very unique kind of rover. Most people wouldn't even call it a rover. So there's no external moving parts in the system. It's really just these 3 internal actuators that can cause it to hop. Now that was a demo in our lab, which of course is under Earth gravity. So the dynamics are very difficult to emulate when we're trying to target bodies that have much weaker gravity. So that was another real challenge that I faced in grad school, is once you're dealing with the space environment, which is very foreign to what we have to work with in our laboratory, we have to get a little creative with how to mimic the space environment. So this is a neat way that we set up an experiment to recreate the microgravity that we expect on asteroids and comets. NASA at the time was operating its own spacecraft, its own C9 aircraft in this out of Johnson Space Center. And essentially they take this aircraft and fly big parabolic arcs, about 30,000 vertical feet up and down. And what that does is it gives you about a 20 to 30 second window where you can test reduced gravity concepts. So a lot of technology developed for space needs to work in a reduced gravity environment. So there's all kinds of engineering systems that want to test in this vehicle. So we developed a box, this payload box here, which was essentially an experimental apparatus where inside we had our prototype rovers. There were 2 of them. And we were given, over the course of 4 days, we flew about 200 of these parabolas. So that's a few hour flight per day each day. And the nickname of this flight is the Vomit Comet, for obvious reasons, because it's basically a roller coaster. And I can attest that it lives up to its name. It's quite a ride. So it's a really fun experience. And I'll show you some of the videos we captured from this rover hopping in the reduced gravity. So what you're seeing here is a GoPro mounted inside this experimental box. And on the bottom right, on the bottom left, there is our prototype. And you can't actually see the internal reaction wheels, but what's happening here is we pre-spin these wheels, and then by applying the brake, we can hop. And in this setup, we can observe what would actually happen in reduced gravity. So the contact physics between the robot and the terrain are very interesting to observe in reduced gravity. So that was an example of a hop. I'll play it one more time on a simulant material that some scientists at JPL developed to mimic what we think the surface of a comet might feel like. It's essentially an aerated concrete. But we did test on a variety of materials. This one was a box with just loose sand in it. So you can see the different sort of dynamics that happen here. Can someone nod if these videos are playing okay for you? Okay, great.
Yeah, we can do it. We can see them.
So in the case of loose sand, the dynamics are quite different because it's essentially pushing this fluid, because the sand becomes fluidized in microgravity. It's really fun. It's a mess to work with because we had to clean this whole thing up after every flight. But to see the ability of this rover to hop in loose sand was really interesting. Now, this was an interesting maneuver that we just tried on a whim. And this was, we dug the rover into the sand, so it was sort of stuck, just to see if we could escape. And then we applied just a highly energetic torque to internally. And you could see this, we call this the tornado maneuver because it created like a tornado of debris as it hopped away. So that was a very fun campaign. And it really taught me a lot about how to test, how to develop test beds for that we can use on Earth to observe behaviors that we would expect in space. Another cool part of my job is sharing this with the public. So this was a fun event in Washington, DC. Every year there's an event where NASA showcases a lot of its technologies that's being developed to Congress. And so there were a lot of members that were kind of going to stands, and I showed some Congress members how the robot worked, but I also got the chance to meet a couple kids that were very excited. And so I developed this little remote controller that anyone can operate. And essentially it's just a few dials and buttons. And it was a real hit with the kids. So I really like going to these public outreach events and getting the kids excited about this stuff. This was another very impromptu event that we were just kind of, after that event on the Hill, we went to the Air and Space Museum, and we just happened to we just brought our robot with us, and someone asked what it was, and then it turned into us giving a demo, and then we amassed this big crowd around us, very interested in the concept. So that was a fun experience. Okay, so that was really, so my work at JPL was essentially developing the controls for this robot. How do we get around? And it still hasn't been integrated into a mission concept that NASA plans to fly yet, although we are working with scientists to understand what kind of instruments we can put in this rover for different targets. I mentioned Phobos, so Martian moons is an interesting idea, an interesting target concept, but also some near Earth asteroids that could be potentially hazardous. Impact hazards for Earth are also high priority targets of exploration that we might send this concept to one day. So the other neat thing about this was it was a constant interaction between JPL. I mentioned that this was a partnership between JPL and Stanford. And through that 4-year PhD experience, I was traveling to JPL, and it was a real great way to get my foot in the door. And after I graduated, I ended up moving to JPL, and I've been there since 2018. And so at JPL, which is down in Pasadena near Los Angeles, I encountered what I call the wonderful world of robotics. It was really a roboticist paradise because there's hundreds of people developing concepts, rover concepts for exploring all kinds of bodies in the solar system. So not only did I get to learn about all the different celestial objects in the solar system, Mars, Venus, the moon, Jovian moons, I knew some about small bodies, but then I also got to meet all of these other robotics technologists like myself who are trying to develop systems that allow us to explore these very foreign environments. So I'm just highlighting a few of them here. On the bottom left, if any of you had been in the seminar about a year ago when my wife gave a talk about Moondiver, these pits on the moon, that was actually how we met. And I was developing the rover at the time. And that's the one in the bottom left there. It's a tethered rover that essentially rappels down into a lunar pit. And so we're hoping to repropose that to NASA next year. And if all goes well, we could fly that not too far in the future. Some other concepts are highly articulated systems. So the terrain on planetary bodies can often be very rough, and to go to really interesting places for geology often are not the boring flat surfaces. So there's been many rover concepts developed to try and extend the reach of our instruments and put cameras really near the interesting geology on vertical surfaces. So robots that climb, robots that have highly articulated suspension that can drive over very rough terrain. And then rovers that don't even, touch the ground necessarily, like balloons, I'll talk about in a bit, and other concepts, and helicopters. You guys have probably seen some of the interesting news around the Mars helicopter. A lot of my colleagues have been working on that, and that is a whole new paradigm for exploring Mars. And JPL is now thinking about how to exploit rotorcraft for future Mars exploration that are larger and have more capable payloads. So one interesting thing about being at JPL is not only are you surrounded by engineers doing all this stuff, but there's a bunch of scientists here too. So you can not only work hand in hand with other technologists that have different expertise, but you can also talk directly to many scientists who are really directing these missions and trying to propose missions of their own. And the interaction between the scientists and engineers at JPL is really how the new missions are born, because scientists typically have an idea of what they want to explore in the solar system, but not necessarily how it might be done. And then engineers and technologists trying to come up with mission concepts. So having worked on asteroids and small bodies just prior to this, I talked with some scientists at JPL who work on this subject, and we got into a lot of discussion about the real unknown about these bodies is what they look like on the inside. We've sent quite a few spacecraft at this point to various small bodies in the solar system, some to comets, some to asteroids, the Martian moons. And from those missions, we've developed a picture of their surface environment to pretty high resolution and observed that they're highly diverse, but we really don't know anything about their internal structure. We have good models for Earth's internal core and the mantle structure, and to some extent that has been extended to other large planetary bodies with high gravity. But these small bodies that don't have enough gravity to coalesce into a spherical shape, there's a lot of uncertainty about what they actually look like on the inside. Are they completely loose aggregates of rubble? Do they have a solid core, like a planetesimal core? And the answer is probably different depending on the body you're talking about. So this got me thinking, how do we actually develop a technology to explore inside the surface? And so typically what you do is you look at state-of-the-art, what we do state-of-the-art, and by and large, the three methods that we've used to understand the interior of Earth and to some extent other planetary bodies are radar, seismology, and gravity science. Radar being essentially a method of emitting a signal and looking for reflections. And by measuring those reflections, you can infer the structure. Seismology is essentially listening through mechanical coupling to the surface and using inversion techniques to understand what the internal propagation of sound waves looks like. And gravity science is really a uniquely spaceborne concept where instead of shooting something into the body or listening directly, you actually have a projectile, in this case a spacecraft, that is orbiting a body, and its perturbation measures its perturbed orbit is induced by mass anomalies within the body. So, if you ever took high school physics, you probably know the basic model of gravity for a planet is to treat it as a sphere. Well, it turns out all bodies, even ones that are quite spherical, have these higher order terms that are induced by things like mountains and valleys and oceans and glaciers, and all of those different mass anomalies perturb the orbit of a spacecraft. And if we can measure that perturbation, we can infer those measurements. So all of these methods have faced a lot of challenges for small bodies, but my prior work on the hopping rover actually got me thinking about how we might do this for small bodies, do gravity science for small bodies. And so I touched on it a little bit, but just the basic primer on gravity science is essentially we're looking for these mass anomalies by measuring very fine perturbations in the orbit of a spacecraft. Essentially, if it orbits anything but a Keplerian elliptical orbit, there are some non-spherical mass anomalies that you can attribute to those forces that act on the spacecraft. So this is a technique that's been used extensively for monitoring the water cycles on Earth and measuring the crustal structure of the moon. Actually, here's kind of a highlight of how accurately we've measured the gravity fields of different bodies in the solar system. And on the y-axis here is essentially what we call the spherical harmonic degree. That's just a metric for how fine you can measure the spatial resolution of the gravity field that you can measure. For example, Mount Everest would create a huge mass anomaly that could be detected by a orbiting spacecraft. So essentially, the higher the degree, the finer the resolution we're able to measure. And so you can see we only really have high resolution gravity fields for the Earth and the Moon. That's primarily because we use a special technique with two satellites doing relative in relative orbits for the Earth and Moon. But for all of the other bodies, we essentially treat the gravity science as a ancillary measurement that we take by just observing the primary spacecraft. For example, when Galileo went to Jupiter, every time it flew by one of the Galilean satellites, we could monitor its trajectory, and by monitoring it, we could understand the mass, the gravity field of those bodies, but only at a very coarse level because it wasn't orbiting for a significant amount of time. So the key factors that make this possible, and generally we get better gravity field measurements for bodies that are larger, measurements that are lower altitude, because that's where the sensitivity is the greatest to the local mass anomalies, and for longer integrations. The longer you have something orbiting around, essentially you're building up signal that you can use to estimate the field. So these three things are what makes it very challenging to do this for small bodies, because small bodies, because they have an irregular shape, they're highly non-spherical. It turns out that creates unstable orbits. You can't get a spacecraft to orbit at a low altitude because it would go chaotic and then crash into the body. So for that reason, all of the asteroid missions of the past, the spacecraft has to orbit at a very high altitude, and we're not able to measure the gravity very well. So that's when we had this very interesting observation from a recent mission called OSIRIS-REx, which was a NASA mission to asteroid Bennu, a near-Earth rubble pile asteroid about 500 meters in diameter. And they actually discovered particles being actively ejected from the body. So the body is essentially a loose aggregate of rocks and of varying size, from all the way from millimeters up to tens of meters in size. But the thing we didn't expect is that these particles were being constantly ejected and recolliding with the body. So essentially, imagine meter scale boulders, centimeter to meter scale boulders being actively thrown off of this rotating asteroid. And this is one picture that shows some of those particles. Now, the interesting thing some of my colleagues were able to do from this was to track the motion of those particles that were in close proximity to the body and measure and infer the gravity field of the body with those low altitude measurements. And it turns out they were able to understand that Bennu is actually composed of a solid core and a loose, low density bulge on the equator. So that was only possible, that kind of measurement was only possible because they could track these particles that were at very low altitude. But the problem is we don't have these kind of lucky ejections, particle ejections at every body. So the concept that I proposed and that I've been working on for a few years now, we've called it gravity poppers. Essentially, the idea is to take the hopping rover concept that I described to you before, shrink it down so that it's a very small scale probe and deploy many of them to the body. And they would just constantly hop around the body randomly, sort of like a random swarm. And the mother spacecraft could maintain a safe, distant orbit and monitor and track all of these probes as they're hopping around the body. And by observing all of their dynamics for an extended period of time, it could build up a very high resolution map of the interior structure of these bodies. So this is a cool animation we put together just to show you what that would look like. So imagine, I think this is 20 or 50 probes that we deploy to, in this case, this is a comet, the nucleus of a comet. And you can't actually resolve here what the probes are, but essentially imagine just a small cube or sphere that is in free fall around the body. And every time they impact the body, they bounce around and eventually come to rest on the surface. And once they come to rest, they trigger another hop using that same kind of momentum device I was describing from before. And the interesting thing about them is they don't actually need to carry any instruments of their own. So they can be very small. All they need to do is be visible to a distant mother spacecraft that's observing all of their motions.
Hey, Ben,
So, yes.
how do you calibrate how much force it could use on some of these bodies without flying away and losing its orbit, essentially?
That's a great question. Yeah, so yes, the escape velocity on these bodies can be under 1 meter per second. So you're talking about so low that you could actually jump off the body and never come back. So we do have, before we send a mission, a rough idea of the size of the target we're going to. And based on our taxonomy of small bodies, we can infer their density from their spectral characteristics. And so we can estimate the mass of the body crudely, but enough to estimate how much energy to put into each hop so that they don't escape. But that is a key question. Let me play this video one more time. And actually, the escape velocity on the body is a little more complicated than that because it depends on where the probes are hopping from. There's not a single speed that would trigger an escape event. And so there may actually be some probes that do escape the body, but the idea is that if we keep the nominal velocity of these hops in an appropriate range based on our calculations, we can tolerate some of the probes escaping and still get a great set of measurements. So this video just shows you what the spacecraft would be building up in its internal memory, all of these trajectories. And by observing weeks to months of this activity, it really has an immense data set that it can use to invert and infer the interior structure of the body. So I'm just going to highlight some of the kind of tech. So that's an interesting idea, but how to actually flesh out if it's actually feasible. So I'm just going to take you through three of the concepts, three of the dimensions of the problem we considered. And this is one where it really has a lot of overlap with astronomy, actually, because essentially this is a problem of tracking point sources of light that are moving around a body. So a lot of the literature in the field of asteroid tracking from Earth-based telescopes was really helpful in understanding how bright these objects need to be to have a high enough signal to noise ratio so we can centroid quite accurately. So essentially we need to have onboard LEDs on these probes that strobe in synchronously with the camera that we're taking a picture. So imagine the mother spacecraft a few kilometers distance taking images at a regular frequency, and every time it opens its shutter, the probes would strobe their LEDs, so you would get a very bright signal. And by using an appropriately matched optical and frequency filters, we can increase the signal of these probes and pick them up from very far away. Imagine trying to see about a tennis ball sized object from 4 kilometers away. So it's very far away. So you're not actually resolving the probes. They just appear as point sources of light. So we kind of use these first principle physics type equations, a lot of which are from the field of astronomy, to derive these kind of requirements on the system. So from that, we could essentially determine how brightly we needed to flash the LEDs on the probes. And then we also used dynamic simulations, because that's really all we can do here before we actually send a mission to understand the dynamics. So those animations I was showing you before are actual dynamic simulations that we use to estimate the gravity field. So we simulate the whole mission and simulate all the images that the spacecraft would take by using artificial rendering techniques. And then we can run some statistical studies of how accurately we could observe the gravity field. The problem with this concept is that gravity isn't the only force acting on the probes. The photons from the sun create a pressure on the probes that are kind of a disturbance force. There's also other disturbance forces like micrometeorite impacts. And so there is sort of a noise floor that we wanted to understand how deep that went. So it turns out from our simulations, we could estimate a pretty high resolution gravity field. This image on the bottom left gives you a sense for the spatial resolution that we could infer the mass distribution on the body from this kind of mission. And so we can now do really cool things like not only estimate the mass of the whole body, but estimate mass of single boulders on the surface. We can also locate voids that may exist in the subsurface. And this is all very interesting for the planetary defense community, because as we develop deflection strategies for potentially hazardous asteroids, a key uncertainty is how these objects might break apart if they hit the atmosphere. And so being able to probe the internal structure in this way would be really valuable for designing those kinds of deflection missions. And this is what the probes would look like. At this point, it's still a very early concept, so we don't actually have functional probes, but just to give you a kind of a sense for what we were imagining, they would be about 5 centimeters, 2 inches on the side. They would be about, there you can see a standard soda can for scale reference. So they're very small. They have a couple batteries inside and really just an array of LEDs that they use to flash. And of course, the internal momentum device for hopping. So imagine taking a few dozen of these in a canister that looks something like this. This is just one way it might be realized. Of course, there's many parameters at play, but this is just a small 10-kilogram instrument that we can now bolt onto any mission that's going to a small body and deploy this swarm of hopping probes, and using our tracking camera, start to refine the gravity field. So that's kind of our artist conception of what it might look like. So let me see. Yeah, okay. Yeah, so here's kind of the hero shot of what the system might look like at the body. It's deploying all of these probes. I'm going to pause here because we're going to talk about Venus next. If anybody has any questions about this, the small body domain in general, or the hopping systems that I've been talking about.
I wonder, do you get the probes back, or do they just stay after you've launched them?
They just stay.
Okay.
Yeah, so we could have an end of life scenario where we tell them to hop fast enough so they escape away from the body and then they just float away into space. Or we could just have them rest on the body for all eternity.
Thank you.
And this is Bruce. I have kind of 2 related questions. I guess the first is, I know these are just plans right now, but how close are these kind of gravity poppers to kind of being a future mission? I mean, are we talking about maybe never, or 5 years from now, to explore an asteroid, or, what's the prognosis there?
Yeah, that's always the $1 million question with technology. And I'm confident that this brings a unique capability to make a measurement that can't be made any other way, really. And so it's really the path from here to a mission is really a matter of opportunity and finding a good science champion for it. So everyone's very busy. So taking on like a new concept like this that's kind of high risk is difficult. And so it's really on the onus of the technologist to kind of market the concept to scientists. And so I've been having more and more conversations and getting people excited about it. Right now we have a scale from 1 to 9 at NASA, from back of the envelope sketch to it's already flown in space. And this is right around TRL 4, right in the middle. So the next steps would be to develop actual flight qualified prototypes. And from here to a mission, it could be anywhere from 5 to 15 years, or
Okay.
never, honestly. Depends on it. A lot of it depends on political will too. I mean, there's only so much money at NASA, and so we have to be strategic about what we send and what we don't send. So it might just be that the winds are blowing in a different direction in certain times. So anyway, that's a hard question to answer, but my short answer would be 5 to 15 years.
And kind of the sort of the related question to your hedgehog hopper, when you have this shift in angular momentum and then you brake to create the hop, is that kind of episodic, or can you, at least in concept, kind of coordinate the hopping? So it would be a steady kind of hopping on a surface rather than just a hop and then a hop. You know what I mean? I don't
You
know if
mean
that makes-
something that is more continuous contact with the surface?
Yeah, exactly. That rather than just, a periodic or episodic hopping, it could literally be coordinated by, constantly
Yep.
shifting angular momentum, braking, shifting, braking, I mean,
Yep.
just, I know it's all has to be autonomous, but
Yeah, so we developed different, what we called motion primitives, different types of mobility modes, you could say. Hopping is one of them, but you're right. You could, if you actuated the reaction wheels in a different way, you could just flip about one face without losing contact with the surface, and then kind of do a stepwise mobility where you're kind of flipping end over end. And you can also turn in place, point north, point west, point east to point an instrument. So yeah, there's actually a lot of different kind of mobility modes you can achieve with just those 3 actuators.
great. Thank you. Thanks.
Okay, since I seem to have some kind of timer here that's telling me to go talk about Venus, let's talk about Venus. So Venus is very hot right now. We have, if you guys have heard, we have 2 new missions in the works for exploring Venus. Veritas and Da Vinci, which are both orbiters, but some of them do have dropped probes. Venus has been explored back since the 80s, really primarily by the Russians. The Russians have had a lot more success in the early days with Venus than NASA has, but there's a new momentum building to explore Venus. Some of it driven by the new tenuous discovery of phosphine in the atmosphere. But there's just a huge contingent of volcanologists that just think of Venus as a very interesting place to study volcanism in the solar system. The problem is Venus is shrouded in global cloud layer, so it's very difficult to image the surface without actually going there. So if you were to remove the clouds, this is what the surface looks like. And this was an image it's a composite image that was derived from radar. So you can penetrate through the clouds with the radar from orbit, but you can only get so good resolution. I think this is, I don't know, either I would say 100 meters to 1 kilometer per pixel. So quite low resolution. So the next wave is really to bring the kind of exploration capabilities we've done on Mars to Venus. And so one concept, so the challenge with getting to the surface, of course, is it's just an oven. It's about 500 degrees Celsius. So it would almost melt aluminum. It would melt lead. The pressure is enormous. It's 90 times our atmospheric pressure. And you have to deal with sulfuric acid clouds as well. So a myriad of challenges. And no one's really figured out how to create a rover that can last for more than a few hours on the surface without dying. And so what JPL has been really developing for the past 20 years is instead to use balloon-based concepts. So this isn't really a rover per se, but it does have a lot of robotic technologies in it. The idea is to keep a balloon aloft in what we call the Goldilocks zone in the atmosphere, which is a fairly benign pressure and temperature, from which we can make a lot of in situ measurements in the clouds, but also look down at the surface. So I'm going to skip here. Yeah, okay. So the real game changer would be if we could design a balloon that can vary in altitude in the Venusian atmosphere. So just a fixed balloon would, as the Russians did in the 80s, maintain a steady altitude, which limits the kind of science you can do. So JPL has really been developing this variable altitude balloon concept for the past 10 or 20 years. And I'm going to show you the basic concept there. So the idea with a variable altitude balloon, and these have been fielded a lot on Earth, these concepts, is essentially a balloon within a balloon. So the outer balloon is what we call a zero pressure balloon. So there's no pressure inside the balloon. It's just filled with helium at ambient pressure. But inside of that balloon, there's another balloon that's a super pressure balloon. And that can, it's strong enough to hold a pressure above ambient pressure. And essentially by exchanging gas between these two balloons, you vary the total volume of the system. And thereby you can go up and down in the atmosphere. And the range that we're targeting on Venus is about 50 to 60 kilometers. Any higher and you run into issues with radiation, and any lower, the temperatures become too hard. So that's really the Goldilocks zone, is the 50 to 62 kilometers. And so this is an experiment in a big hangar. A couple of my colleagues testing a prototype, about a 4-meter balloon. And there's a pump, essentially a pump that pumps the helium between the super pressure balloon and the zero pressure balloon. And by adjusting those, the fill ratio of the two, you can get it to either go up or go down. So the interesting thing about that is the winds on Venus blow in different directions at different altitudes. So you can, while you don't have any direct control, like a dirigible would to fly laterally, you can control coarsely the direction you go by the altitude that you sit at, and thereby moving with the prevailing winds at that altitude. But there's still a problem with these balloons that a colleague and I were trying to solve, and that's that they still can't get below the clouds. Turns out the clouds, the thick clouds on Venus, are around 47 to 52 kilometers. And we know that quite well from our previous missions that had drop sondes that were dropped from these high altitude balloons and went down to the surface. But the problem is we can't really fly a balloon that low below the clouds because it gets too hot and we don't have enough solar energy for the balloon. And so the question is, how do we extend the reach of these, we call them aerobots, variable altitude balloons, to go even lower so we can start imaging the surface? Because from this altitude, we can't actually image the surface in anything but far infrared or radio. So that's where my colleague proposed the idea of a tow body. Basically, this is a camera on a string. Imagine a aerodynamic body that houses an infrared camera, and it's attached to the balloon gondola through a long multi-kilometer tether. This tether is slowly unspooled from the gondola, so this tow body is lowered, and it's lowered so that its altitude is below the cloud layer, and it can start imaging the surface in IR. So this is a totally new concept for Venus, but actually on Earth, we've used tow bodies to do a lot of different things, both for aerial tow bodies and underwater tow bodies. And so we were able to leverage a lot of lessons learned and in studies, published studies from these previous works to essentially understand the feasibility of how we might do this on Venus. And the key challenge with Venus is, as I mentioned before, the winds at different altitudes vary. So if your balloon is parked at 52 kilometers, let's say, traveling with the prevailing winds, as soon as you start to lower a mass on a long tether, it will be subject to a relative wind shear with respect to the balloon. So the question is, can the tow body actually descend to the altitude you want, or will it just get blown behind the balloon? So that's where we did some modeling. So turns out that a tether, even a very thin tether, like less than 1 millimeter in diameter, has a very high drag coefficient. It turns out as the wind shear increases, as you go down, the drag is dominated by the drag on the tether, not on the tow body itself. And so there are some interesting scaling laws that emerge. The thicker your tether is, the more drag is induced on it, and the more forces are on the tether. Therefore, you need a thicker tether to withstand that strength. So there's kind of a runaway effect in the scaling laws, and it turns out to just be on the border of possibly feasible to lower a tow body 5 kilometers, from 52 kilometers down to 47 kilometers. And this shows you some of the different profiles the tether would take as you lowered it. And the animation on the right kind of shows you real time how the tow body would trail the balloon as it's descending. So it turns out you actually need about 10 kilometers of tether to lower yourself about 5 kilometers because of the lateral displacement. And so what does the tow body actually look like? Well, typically what we do at JPL is we start from what it needs to do, the objective. So essentially it needs to house a camera, and that camera needs to be maintained at a certain temperature. And it can only be have a certain amount of mass and volume, and it requires it needs to be pointing down with a certain amount of stability. So essentially you start to compile all of these requirements and try and find a system that meets them all. And one concept that we've initially thrown around, this is by no means set in stone, is this kind of Tintin rocket looking thing where, oops, sorry, I don't know why my slides are auto advancing. So this is about 20 inches long. Its real main job, as I said, is to house this infrared camera that's pointing down at the surface. But it also needs to have onboard power storage, and it needs to be highly insulated thermally from the environment, because when you descend down to 47 kilometers, the temperature is above 100 degrees Celsius. And we need this camera to stay at about 25 or 35 degrees Celsius to image. And so thermal is a big problem, and also attitude stability. We mount this whole contraption within a passive gimbal that allows it to decouple rotationally from the turbulent perturbations on the tether. So we're currently working with a team, a student undergraduate balloon team at Stanford University, to start fielding some of these prototypes and understand the feasibility through more experiments rather than just pure modeling, which is all we've done so far. All right, so that's all I have to say about the Venus project. This is actually still ongoing. We have active proposals in right now to continue this work. And like I said, these aerobots are becoming more and more popular concept for next generation Venus missions. So we actually think there's a pretty good chance that this technology could be infused into a next generation balloon.
So do you see these going into the next 2 missions, or maybe after that?
No, Veritas and Da Vinci are both fully defined. In fact, at the time of the proposing, there's not much room for modification, and they're not balloon concepts. So there are just orbiters. Da Vinci does have a drop sonde, I believe, or maybe a few of them. And those are interesting for getting a single transect through the Venusian atmosphere, pressure, temperature, and composition. But of course, they can't give you a global coverage. This concept, the reason the balloon is so attractive is because you could get near global coverage as the winds blow you around the body. So yeah, no, it wouldn't be on these new missions, but NASA is considering a New Frontiers class mission, which is a little bit more expensive than the two that I just mentioned, or even a flagship mission, a la the Mars Curiosity and Perseverance rovers, which are much more expensive. And for that kind of cost, you could fit a lot more technology into the mission. So those might be missions that are formulated in the next decade.
Ben, question. Has there been any proof of concept testing anywhere on Earth with aerobots, carried by balloons in certain environments where, enormously
Yes.
high winds, et cetera, et cetera?
Yeah, so the variable altitude balloons, yes, a lot. There have been a lot of variable altitude balloons. In fact, Google for a while was pursuing a internet service, a balloon-borne internet service, where they could vary the altitude of their balloons with these little transceivers or these broadcasting devices on them. So variable altitude balloons have been flown a lot on Earth, but tow body is less so, especially tow bodies dangling from a balloon. There have been plane-towed tow bodies, military grade, and then a lot from underwater vehicles for doing, towing behind a boat. But balloon-borne, not so much. We have a hardware prototype of this concept you're looking at here, and we've done some very simple tests near JPL, just essentially hanging them on a kite, or even just dangling them outside the window of your car to understand the attitude stability. But really, these aren't going to. The real proving ground for these is going to be to fly them on a balloon. So that's why we're now starting to work with the Stanford balloon team to get them to help with some flights.
A quick question, if I can ask. I'm looking at the tow body national design, notional design that you have up there, and it would seem like even with a vacuum gap and insulation, ultimately it would seem this is going to have a pretty short lifetime because you don't have any options for thermal dissipation. Are you looking at anything for thermal dissipation?
Yeah, so that's a great point. And the one thing I glossed over with this would attitude cycle. So we would only go low for a short period of time, and then we would reel it back up to the balloon height. And at that altitude, it's much cooler. And one trick we do often in space is essentially use these thermal batteries, which is essentially a wax that melts. So you can design these paraffin wax batteries to hold the temperature for much longer than the thermal mass of just changing temperature. And so we can get, we think, up to 50 hours of imaging at this lower altitude at 100 Celsius. But you're right, there's no way to dissipate any thermal. So that's why we have to reel it back up to refreeze the system.
Thank you.
Yeah. That's one thing I didn't have as big of appreciation for before I joined JPL, is how much thermal considerations really drive a lot of robotic concepts, because space is both hot and cold.
Ben, really naive question, okay, but following up on that, why not test these over areas without active volcanoes where there's gases, there's wind shear, there's enormous amount of heat? I mean, it's not Venus, but
that is exactly the proposal that we have, and that's pending right now.
Okay.
We are proposing to fly this over the Icelandic volcano. It was active. I forget the current status, but with an IR camera, you really want to go image a hot source.
Right.
And so, yeah, we would like to go and field this over an active volcanic site.
Thanks. Thank you.
All right. Well, I've talked about hoppers on tiny worlds, talked about balloons in harsh Venus atmosphere. Now I'm going to switch topics to the last concept that I've been really involved in for the past couple of years, and that's ocean worlds. So from Galileo and even before, we've started to understand that many of the bodies in our solar system have within them liquid water oceans. And one of the main charters of NASA's scientific endeavors is to understand if we're alone in the universe. So in addition to the SETI type investigations where we're looking for signals from other star systems, we think that there could be a good possibility that some of the bodies in our own solar system neighborhood might have had or currently have life on them. And the mantra for searching for that is to follow the water, because at least for Earth terrestrial life, it all requires water, at least at some point in its life cycle. And so the discovery that a lot of these icy moons, especially the Jupiter and Saturn's moons, have within them a global liquid ocean underneath their surface. They're very far away, so it turns out you can't have stable liquid water on the surface, at least not for very long. But because Jupiter especially is pumping energy into its moons through their elliptical orbit, through the tidal flexing of the body, it actually creates enough energy to maintain a liquid interior. So one body of, so NASA has kind of this main theme in its scientific exploration, the search for life. And sort of how we've matured through our Mars exploration program, starting with flybys and then orbiters and then landing on the surface and then roving around the surface, kind of this progression of exploration. This kind of maps out the progression of exploration that we envision, or NASA envisions, for ocean worlds. We have a big flagship mission coming up called Europa Clipper, which will fly to Jupiter and orbit Jupiter, but fly by Europa at a very low altitude many times and characterize the body. But beyond that, JPL is also working on a lander for Europa, which isn't yet a funded mission, but could be soon and might even launch within a decade. But the question is, how do you actually get to the liquid water? So that gets you to the surface, but the actual liquid water where life might be thriving currently is actually under a huge icy shell. And that the nature of the interior profile of these bodies varies from body to body. Some of them have a silicate crust, some of them have pure ice crust. And so the reason Europa is interesting, particularly for the search for life, is that we think that the global ocean is underneath a pure ice crust. And so this is a picture of Europa from Galileo, where you can see a lot of the stress cracking that's induced by Europa's eccentric orbit around Jupiter that stretches it and creates these stress marks. But what our models suggest the structure of Europa is an ocean that could extend down to 150 kilometers below the surface. But there's an ice cap on top of that, which may be anywhere from 10 to 50 kilometers. And we don't yet have enough data to understand the thickness of that ice layer with a lot of precision. But Europa Clipper is this next mission that's gonna launch in a couple of years will have a couple of instruments on it, including a radar sounder and gravity science to measure essentially how thick this ice crust is. So the reason ice is interesting is because we know how to get through it relatively easily. All you need is a hot source. You just need to melt through it. And it turns out glaciologists on Earth have used thermal probes to penetrate ice glaciers and access the base of the glaciers for decades. And so we actually have a long history of technology on Earth that has been able to penetrate kilometers of ice. Of course, we don't have tens of kilometers of ice on Earth. I think the deepest part of Antarctica is only 3 or 4 kilometers thick. But nonetheless, penetrating ice is a much easier prospect than drilling through rock that's tens of kilometers. And so this is the mission concept I've been working on for the past few years. And it's what we call it is it's a cryobot. Essentially, think of it as a self-contained drill which at its core has an RTG, which is essentially plutonium-238 which is manufactured. It's a specific isotope that just dissipates heat passively. And this is the radioisotope that's at the core of a lot of our RTGs that power the spacecraft in the distant parts of the solar system, where we house the plutonium in a central core. And then around that, we have some electric devices called thermoelectric devices that use the temperature difference between the hot interior and the cold environment to generate electricity. So for this concept, we actually want to utilize all of the waste heat coming off of that plutonium to melt through the ice. So that's the basic concept. Of course, there's a lot of challenges, a lot of technology challenges that we have to solve in order to make a cohesive system work. And so this is our concept art. This is the vision of what the probe might look like when it breaches through the ice-ocean interface in Europa, and hopefully in the vicinity of that, there may be evidence of life. So how do you even start designing a system like this? Well, typically at JPL, we like to start from the top down. Like what do we actually want to bring there first? A probe, a rover, a balloon, a hopper. It's really just a vehicle for transporting instruments that do scientific measurements. So we really have to start with the instruments. What science questions are we trying to address? How big are those instruments? And essentially, how do we design a system around that to transport those instruments where they need to be? So I'm not going to go through this in detail, but we went through an exercise with the science team of defining a hypothetical instrument package that we might want to carry to the ocean of Europa. And the important takeaway from that study is essentially about how big is the system? Are we talking the size of a tennis ball, the size of a car? And so it turns out we think we can do it in about 30 liters or about 50 kilograms thereabouts of instruments. It would be about a dozen or so different instruments measuring seismic waves in the ice shell, but also a suite of biological detection instruments like microscopes that would actually analyze the water in the ocean. And so because we don't yet have a precise measurement of Europa's ice crust, we define a range of possibilities, and these are based on physical models. So on the left, we have kind of our thinnest estimate of what the Europa ice shell profile would be, where the darker blue on top is the cryogenic ice. This starts at about 100 Kelvin or minus 200 Celsius, thereabouts on the surface, and the bottom layer is a convecting warm ice layer. So that would be from 0 C down to minus 20 C. And the relative thicknesses of these two layers is, as I said, uncertain. So we put these bounding cases as a range of possibilities to design to. So not to get too in the weeds, but essentially just to give you the basic principles of how a cryobot works. It's essentially a cylindrical vessel. At the core is this RTG, and just imagine it as a heat source that's constantly kicking out heat. And we need to redirect that from the inside to the environment. So essentially we need to melt the ice beneath the probe. And we do that by transporting the heat from the RTG down to the nose of the probe, which melts the ice. So think of that as the useful work. But then it turns out when the ice is cold, it's constantly wanting to refreeze around the probe. And if it turns out if you don't apply heat radially outward from the sidewalls of the probe, the ice will just refreeze onto the probe and it will stall in the borehole. So the key is to distribute the heat in an efficient way so that it melts while also not refreezing into the borehole. And eventually, once the water flows around the probe to the tail end, it will refreeze. So this probe is constantly descending through a contained liquid melt pore that is descending at about a couple meters per hour. That's about the velocity. So it would take a few years to penetrate the entire ice crust, moving at the rate of a few meters per hour. It's quite slow, but actually, if you compare it to some of our Mars rovers, because it never stops. It's actually not that much slower than the rovers. So the key is we're going through different temperature ices. So at the surface, when we have cryogenic ice, most of our heat is actually lost through this lateral diffusion that we have to supply to prevent the borehole from refreezing. So we have less heat available for melting. Whereas once we get to the warmer ice deep down, there's less of a tendency for refreezing, so we can move faster and utilize most of the heat in the front end. So
And
it's this interesting.
Is this
Yeah.
cryobot tethered or is it free?
So I'll flash how our communication strategy in a second. We will be deploying a thin optical fiber about the thickness of a human hair. Think about 100 microns thick.
So how do you keep the borehole from freezing around that fiber optic cable?
It will freeze around it, and that's okay. We do that often on terrestrial melt probes. The fiber will become frozen in the ice.
But then how does the probe keep descending if the cable is frozen?
Oh, I'm sorry. It's spooled on the probe. So it's constantly being paid out from the back end of the probe.
Okay,
Yes.
thank you.
Yeah, good point. Okay, I think I'll skip this. Just the high level here is the equations. This is a fundamentally new type of system. Like we've never had to melt through cryogenic ice on Earth. It's a totally foreign concept. So we needed some way to relate the physics of what's happening to something more familiar that people are more aware of. And we found a very striking parallel between the physics of a cryobot and the rocket equation. The basic principle of rocket is you need a certain amount of thrust to get you out of the gravity well of Earth. And the same kind of principle holds for a cryobot. Unless you have a certain amount of power, thermal power, dissipating from the probe, it will just conduct through the ice and not actually start melting. So you need to meet a minimum threshold heat power in order to actually start melting the ice, or else you're just going to conduct it away. And so that has been, we've used these thermal models to guide how big our RTG needs to be in order to reach the ocean. That's the basic message here. So, okay, once we define the environment and the payload, then we need to kind of break out what the key technologies are that need to be developed. And what we've been focusing on are these three systems, these three subsystems of the probe. The mobility system, which is essentially how it moves through the ice. Then the thermal system, which is kind of hand in hand with that. That's how does it get the heat away from the RTG in a safe manner. If you don't conduct the heat away from the RTG to the environment effectively, you could overheat the whole system and it would just fry. And then finally, we need to communicate. And that's one of the biggest challenges. How do you get data back through a 10-kilometer thick ice shell? And so I talked about the optical fiber, but we also are developing transceivers that are deployed behind the probe as it's descending that relay the signal, both through radio frequency and through acoustic transducers that relay the signal to the surface. So I'll just show you some highlight videos from our testing. These are two prototypes. On the left, I'm showing you a probe that has a heated nose. So this is the nose penetrating through ice, but it also has a water jet, which is essentially a circulating fluid loop that pulls in the melt water from the rear of the probe and shoots it out the tip. And this is really helpful for clearing the dust that might start to accumulate at the tip. You can see at the beginning of the video on the left, there's kind of a thick dust layer that creates sort of a thermal short that prevents it from melting. So the water jet helps to motivate all that particulate and allow the probe to continue melting. On the right, where we were experimenting with the hybrid rotary drill and melting. So you can see initially the system just penetrates through the ice. These are both sped up quite a bit on the right. That this whole experiment is about an hour, so this is sped up dramatically. So the probe is just heating its tip at first, but then what we did is we put a block of salt between these two ice blocks to create a barrier that couldn't be melted through. We defined a list of possible hazards that might exist in Europa's ice shell. And so we think that thick salt lenses might be an issue. And so we're exploring the idea of using a hybrid drill, rotary drill, in combination with melting to help penetrate through those hazards. On the thermal system side, we broke it down into a set of key functionalities. I'll just show you a highlight experiment we did here. So this prototype is a bit different in the sense that this is cryogenic ice. So this ice is at 100 Kelvin. And what this probe is testing is actually the internal thermal management system. So what you can't see is essentially this aluminum tube has within it a mock RTG. Of course, we don't have plutonium to play around with in the lab, but we have a mock RTG and a pumped fluid system internally that redistributes the heat from the central heat source to the skin where it can melt the ice. And then finally is the communication system. So you already asked about that. So yes, we have a multi-pronged approach for trying to communicate in a fault-tolerant manner. So in case the optical fiber fails, we have a backup option. And so we really break that into the two approaches, either tethered communication or free space communication. And the tethered could either be through copper, using some kind of protocol like DSL protocol, or through an optical fiber. It turns out the optical fibers can transmit an enormous amount of data through a very, very thin fiber. We're talking 125 micron thick wire, and you can get gigabit data rates. So it turns out 40 kilometers spooled up of optical fiber is only about a 2-liter soda bottle in volume. So we can accommodate that whole spool on the back end of the probe, and it's actually not a huge impact on the system. But in case that frozen in fiber fails, let's say there's some tectonic activity that causes it to shear, we want to have a backup option using free space communication. And so we've been exploring the transmission of radio waves and acoustic waves through ice of different temperatures. And it's a really interesting problem because there's different types of attenuation depending on how the signal is being transmitted. And so we actually think acoustic communication, which is what's primarily used underwater with submarines as a sonar and acoustic communication, because RF is just so heavily attenuated in water. And it turns out it's also heavily attenuated in warm ice. So we actually are going to, as the ice warms up from the surface to the bottom, at some point we will transition from using radio frequency antennas to acoustic piezoelectric transducers, essentially chirping through the ice shell. And we're only talking about data rates on the order of 100 to 1,000 bits per second, which is pretty low. But keep in mind, this thing is melting over the course of about 3 years to get from the surface to the ocean. So we have a lot of time to trickle up data through the ice shell, and there's not a lot of activity until we get to the bottom. And then once we get to the bottom, we allocate a few months for the science campaign. Okay, and that's what the back end of the probe would look like, where we have these 3 repeaters that are deployed off the back end, along with the spooled optical fiber. So here's my last slide. This is just a summary snapshot of what our whole cryobot architecture looks like. At the core is basically the reason we're going is a science allocation. So those that instrument slide I showed you was very important because that defined essentially how much volume we needed to allocate to house the instruments. And then on the front end of the probe is really the business end of the probe. That's the RTG, where at its core has these plutonium ingots, and around are the thermoelectric power generators. And then all of these pipes you see are the internal fluid management system that pull the heat away from the RTG and distribute it where it's needed around the probe. And then on the back end is the communication system, which, as I just mentioned, houses a spooled optical fiber, as well as a few deployable repeaters for communication. And all designs that we make in NASA have to have what we call margin. Essentially, all of these are based on estimates. So we need to allocate some margin in case some of our estimates grow, right? So we have to have some unallocated system margin. So all in all, this is a pretty big system. It's about 300 kilograms. You can see a human there for scale. But it's about the same mass as the lander we're planning to send to Europa. So it's not unrealistic, but it would be a very expensive flagship mission. Think on the scale of the Mars rovers or even more. It's about 4 meters long, so it's quite tall, and 9 inches in diameter. And we think we can, depending on how thick the ice shell turns out to be, we would size the RTG appropriately, and we think we can get through the ice shell in about 2 to 5 years of melting. So yeah, that's all I wanted to say about the cryobot. This is one of the projects I'm most excited about, because I think it's really our best shot at trying to find life in our solar system, because it's the only place we know of where there are active, where there's exists liquid water that has the right gradients of chemical and heat energy to possibly have a life genesis event outside of our Earth system. So I think this mission concept is gaining momentum in NASA, and where NASA is funding many technology development efforts, both at JPL and other institutions, to flesh out some of these more risky concepts. So anyway, with that, I'll stop and take any questions you might have.
I get a quick one. It would seem to me that you guys must have looked pretty closely at the material densities in the ice and water. I mean, since there's no propulsion system on the probe itself, you want it to continue to be able to make its way downward.
Yeah.
Could you talk about that for a half second? Or?
Yeah. So the bulk density of the probe is about that of aluminum. So it's negatively buoyant. So even under the reduced gravity of Europa, it still sinks within the melt pore. So it's always applying a pressure to the tip to melt the ice, because the surrounding melt water is at about 1 gram per cubic centimeter, whereas this is more like 2 or 3 grams per cubic centimeter. So it's basically a gravity-fed system.
Thank you.
I have a question about how much radiation does the plutonium give off? And if the whole goal is to find life, are you going to alter life with that radiation?
That is a great question, and something I didn't know a lot about and was concerned about initially too. But as it turns out, all radioactive isotopes have different radiation characteristics. And it turns out this particular isotope that NASA uses for RTGs, plutonium-238, is fairly benign. It only takes about 1 millimeter of heavy metal to shield all potentially hazardous radiation from escaping from the core. So everything outside of the RTG won't actually see any radiation. And we have the whole RTG housed within a very thick pressure vessel, so it can take the ambient pressure of the deep ocean. So it's safe and completely decoupled from the environment. But planetary protection is a whole category that we'll have to consider much more seriously as this concept matures. Essentially making sure we're not killing life or introducing life that we brought from Earth, and making sure that this doesn't contaminate the ocean for the half-life of plutonium is about 80 years. So we would have to make sure that this thing doesn't disintegrate for about 80 years.
Ben, of the couple of concepts that you described, is the kind of the probe and just like the water jetting the preference, or the water jetting and the rotary drilling? And if you do the rotary drilling, is that powered by the RTG or a separate power source? Because it's going to have to work for long.
Yes. So it turns well. Until we go and look at Europa more closely, we still have a lot of very large error bars and uncertainty on what the conditions in the ice shell might be. That's why we're pursuing this range of options. But as we learn more, it might turn out to be more or less benign than our estimates currently. And so the particular challenge that a drill might be required for is the surface, because it turns out, I didn't touch on this, but the surface is in a vacuum environment. So it's actually not melting the ice initially. It sublimates and the ice turns into gas. And it takes a bit of time before, as the probe descends, before the ice refreezes in the borehole and closes off the borehole and creates a pressure that can build up liquid water. So in that initial period, we think we might need to use the drill to get through any surface slag that is deposited. Actually, it turns out Io is so volcanic, it's ejecting material into the Jupiter orbit and depositing on Europa. So a lot of the contaminants that we expect on the surface of Europa are introduced by Io.
Cool. Thank you. Thanks.
Ben, there's a question in the chat. Can you see that one?
Oh, I'm sorry, I'm not monitoring the chat.
Yep, there's one there.
Okay, I'm attaining a master's in computer science at Westchester. I plan to apply for a PhD program. I want to ask you if you feel like a PhD in computer science is attractive to NASA. Perhaps you have any colleagues that have PhDs in computer science rather than, say, physics, for instance? Yeah, that's an interesting question. I mean, because sending a spacecraft to space to do all these things just requires such a multidisciplinary endeavor. It ends up requiring a whole host of skill sets. And of course, computer science is core to that. We have flight computers on all of these systems. I'm not sure what the balance is between the degrees of that JPL hires for in computer science. I know a lot of the software development for the flight computers doesn't necessarily need a PhD. But a PhD is a very specific kind of degree, right? So computer science is a broad field, and I guess it would mostly depend on what flavor of computer science is needed. But if it's developing future technologies for advanced computing systems, that is a huge area of investment at NASA. So absolutely.
Just from an engineering standpoint, question about how hypersaline is that environment in that ocean? Do you have any idea?
Sorry, I didn't quite catch that.
You have a terrible echo there, Dave.
Okay, is that better?
Yes.
That's good.
Okay, how hypersaline is this ocean or this water that we're dealing with on some of these ice moons, and how does that affect the material science that you want to put on there? I can imagine that some of the liquids that are going to be in contact with this vehicle are going to be pretty doggone corrosive. I know what the salt does to my car.
Yep. So there's the question of what salt species might be present. Magnesium sulfate is one, H2SO4, basically sulfuric acid, and NaCl are three likely candidate salt species. And yeah, we don't have a lot. I mean, it's hard to talk about all of these bodies. I'll talk about Europa specifically. We have some models about what ranges might be present. It could be anything from a 1% salt concentration or less to like the eutectic saturation point for salt. But we did design the alloy of the hull of the probe out of an Inconel alloy, which is highly corrosion resistant to all of the species, the salt species that might be present in Europa. But it's definitely like we can't just send any old aluminum probe through the surface because it could be too corrosive. Same with certain types of steel. So we have to use specialized alloys.
So how long are they looking for those things to last in terms of the duration of the mission and beyond that in order not to contaminate the world?
Yeah, that's a great question. It turns out the main structural component of the probe is really the housing of the RTG, because that needs to withstand the pressure. The pressures get to like the equivalent of deep sea ocean pressures. And so that's the main structural element. The rest of it actually can be at high pressure, like electronics are fine living at high pressure, generally speaking. And so most of the probe is flooded. and pressure equilibrated with the ambient. But the main structural component of the pressure vessel would obviously need to last at least the length of the mission. And then we would need to establish a plan for how to dispose of the RTG in a safe way. So either we probably want to, we haven't talked too much with the planetary protection folks too yet about the specifics of the strategy, but I think we want to avoid it sinking to the bottom of the ocean. So making sure it stays at the ice ocean interface is key. And if it is a natively corrosion resistant alloy, it should survive for quite a long time.
Thank you.
Inconel is a common aerospace grade alloy of a nickel alloy.
Ben, I have a question about the balloon. You said there's a balloon inside of a balloon,
Yes.
and for lack of a better word, air inside one, they integrate to move it or to change its altitude.
Right.
Now, would that be pre-programmed, or is that done as needed, or as you want it to move?
That's a good question. I think this isn't, I haven't worked on this area much, but I think we would have some pre-scheduled maneuvers to go up and down. It depends. A lot of it depends on the thermal environment. So if we're too hot, we can regulate by going up. If we're too cold, we can regulate by going down. So there might be like an onboard control loop that adjusts the altitude for that. But we also will have models of the winds in the atmosphere. And because the goal of the mission is to achieve some kind of global coverage of the body, we would probably orchestrate ahead of time some maneuvers where it varies in altitude.
Okay.
Yeah.
Any other questions for Ben?
And you guys, I saw you guys are having Kevin Hand in a month or two, and he's a great guy to ask about the everything to do with Europa. He's a world expert on Europa, so that'll be a great talk.
Okay, if there are no further questions, Ben, on behalf of everyone, I really want to thank you. Really great talk, interesting concepts. Hope at least some of them become reality someday. So thank you very, very much.
That was great. Thanks.
Thanks for your
Yeah,
work.
thank you.
Thank you all for having me.
Really interesting. Thank you so much.
All right, clear skies, everybody.
Yep.
Thank you.
Thanks again.
Bye.